Hello everyone. I would like to thank everyone for making time to attend this presentation. My name is Arjun and today I am presenting a research that was conducted by me and Tarsis Theo at Pantheia. Pantheia is a research consultancy based in Netherlands. Let me dive straight into introducing the research topic. Currently, a large number of logistics companies that deliver packages to customers in urban areas utilize a fleet of diesel vans to move the packages from a distantly located sorting center. Albeit being a proven solution, these vehicles can cause a lot of issues to city inhabitants. They result in air and noise pollution and also cause inconveniences to commuters. The problem is evidently seen in developing countries which have dense urban regions. Learning from developed cities such as London and Amsterdam and keeping in mind with the increase in e-commerce demand, local authorities in these regions are exploring to introduce low emission zones around the core urban regions. These low emission zones, when active, will restrict the entry of high polluting vehicles such as diesel vans, forcing logistics companies to adopt their existing last mile network. In order to continue operations within the low emission zones, one potential adaptation to the last mile network could be the use of transshipment facilities at the border of the low emission zone. The consolidated packages can be cross-docked from a diesel box truck arriving from a sorting center to a light electric freight vehicles. Being completely electric, these light electric freight vehicles can then access the low emission zone and deliver packages. Additionally, the proximity of micro hubs to the customer points also supports the usage of these vehicles as they have limited driving ranges. Although urban transshipment networks can be seen as a potential solution for logistics service provider, they still attract substantial investment for purchasing of light electric freight vehicles and also for establishing micro hubs. Thus, it is imperative for logistics service provider to know beforehand what is the ideal configuration of such networks for their existing business. Network configuration entails the fleet sizes of box trucks, location and size of the micro hubs, and also the fleet sizes of light electric freight vehicles at each of the micro hubs. In addition to this, it is also essential for the logistics service provider to know what is the resulting cost of these networks and also how do they perform. In operation research, a family of optimization problems called as location routing problems, also known as LRP, are traditionally used by network designers to design such networks. But the existing models in academic research are very sophisticated. The reason being that they combine two NP-hard problems, namely vehicle routing problem and facility location problem. Once formulated, they require complex heuristics to solve for real-life scenarios. These complex algorithms limit the understanding of logistic practitioners, necessitating the need for simple algorithms that allow for quick evaluation and comparison against other plausible networks. In the interest of developing something simple, the following methodology framework is proposed. At the core of the framework is the analytical model called as the approximated two-echelon location routing problem. The model's purpose is to find the minimum cost network configuration of the urban transshipment network and also the distance traveled by the vehicle fleets. The step prerequisite to the model uses the customer dataset to generate a scenario which simulates customer demands on a typical working day. The discrete customer locations, their demands, and the location of the sorting center from the generated demand scenario are then fed as inputs to the analytical model. The process following the model analyzes the performance of relevant KPIs with the outputs that is obtained from the model. For each of these three steps, a set of inputs that is relevant in the business context is considered. Unlike the traditional location routing problem, the proposed approximated two-echelon location routing problem is not a single problem. It is a combination of two subproblems named as clustering problem and location fleet size problem. Both these problems are modeled as integer linear programs and have to be solved individually. However, a hierarchical interaction exists between these two problems in such a way that the discrete customer locations and demands from the demand scenario are first fed into the clustering problem, and then the solution of the clustering problem is then fed as inputs to the location fleet size problem. Later, solving the location fleet size problem gives the cost optimal network configuration of the urban transshipment network. Solving the proposed model is done through an iterative solution algorithm, which is explained in the upcoming slides. The first subproblem within the proposed approximated 2 echelon location routing problem is the clustering problem. The clustering problem basically divides the whole set of customer locations from the demand scenario into customer clusters. The number of customer clusters are given as exogenous input to the clustering problem. A set of customer points from the demand scenario equaling to the number of clusters serve as cluster centroids. The other customer points that are not selected as centroids are allocated to each of these cluster centroids. The allocation is done in such a way that the clusters are as compact as possible. Upon forming clusters, a set of parameters that are specific to each cluster is estimated. These parameters include the area of minimum area rectangle bounding all the customers within the cluster, the total demand of the cluster, and the approximate distance traveled by the light electric freight vehicles to serve all the customers within each of the clusters. To find the last parameter, which is the distance traveled by the light electric freight vehicle, a continuous approximation model, which is a regression-based model, is used, and it was developed by Figliosi in 2008. Next, the location fleet size model then allocates the formed clusters to one of the prospective hub locations. The allocation is done in such a way that the minimum number of microhubs are activated from the prospective hub locations, and the capacity of each of the microhubs is not exceeded. The size of the microhubs is decided by having multiple prospective hub locations with identical location and allowing the model to choose how many of them must be activated. Simultaneously, the ideal fleet size of the light electric freight vehicle required at each of the activated microhubs are estimated. This estimation is done based on the combined distance traveled within each of the clusters and the distance that is required to travel from the microhub to the center of the clusters. Additionally, the ideal routes of the box trucks that is required to transfer consolidated goods from the sorting center to microhubs are also estimated by the model. As mentioned earlier, an iterative solution algorithm is built to solve the two subproblems. The clustering problem is solved iteratively with increasing number of clusters in such a way that each of the clusters formed are as small enough to be serviced by a light electric freight vehicle. This is done by considering both the payload capacity and the battery ranges of the light electric freight vehicle. Once that condition is met, the so-formed clusters are fed into the location fleet size model to find the network configuration and the distance traveled by the vehicle fleets. The proposed methodology, along with the analytical model, is then tested on synthetic case studies. 3 case studies were created using VRP instances such that the customer density nearly doubles across them. The demand of each customer within the instance is assumed to be one package of size 42 liters. Finally, two plausible network alternatives are considered because either diesel or electric box trucks can be used in the first echelon. The alternative 1 involves locating microhubs at the periphery of the low emission zone, as diesel box trucks cannot access low emission zone. In the second alternative, the electric box trucks are used to enter into the low emission zone, thus allowing microhubs to be located within the low emission zone. In this slide, I discuss the results obtained by testing the model for the instance with medium customer density. It is evidently seen that the cluster centroids are spread uniformly across the customer distribution to ensure compact clusters. It is important to note that 35 clusters are shown here. Next, the solution from the location fleet size problem in the second echelon is displayed. It is visible that the model chooses to activate only 4 microhub locations from the possible 6 locations. Simultaneously, the cluster centroids are also allocated to these activated microhubs. In parallel to the results in the second echelon, the ideal box truck routes from the sorting center in the first echelon is also obtained from the model. The box trucks only visit the activated microhub locations and not the deactivated ones. An attempt was also made to check the accuracy of the proposed model. The obtained light electric freight vehicle fleet sizes and the distance traveled are compared against the results obtained from exact routing models such as the CVRP. The comparison showed that the fleet sizes obtained at the microhubs are the same irrespective of both these methods. However, The proposed model slightly overestimates the travel distances of the light electric freight vehicles by 6%. Using the ideal network configuration and the distance traveled by the vehicle fleets as obtained from the proposed model, the total logistics cost is calculated. It is evidently seen that as the customer density increases across the instance, the cost also increases. But it is important to note that in medium and high customer density instances, the cost of alternative 2 is much lower than cost of alternative 1. I would like to remind again that alternative 1 uses diesel trucks and micro hubs at the border of low emission zone, whereas alternative 2 uses electric box trucks and places the micro hubs inside the low emission zone. The same trend is also seen in case of average cost per parcel. This indicates that alternative 2 makes use of economies of scale better. Finally, to measure the environmental performance of these networks, the total well-to-wheel emissions from all vehicle fleets are calculated. This is calculated using the obtained distance traveled from the proposed model. They are calculated for both the network alternatives and also compared against the conventional network with diesel vans. The comparison shows that alternative 1 reduces the emissions by 40%, but using electric trucks, as in case of alternative 2, reduces the emissions further to 70%. In this slide, we discuss the research methodology and the results obtained. The proposed model allows to simulate transshipment networks that is likely to be adopted in last mile package delivery, and also finds the approximate cost. Such a method can be valuable for strategic analysis. Complex algorithms that limit the understanding of logistic practitioners is not required. Finally, placing the micro hubs inside the low emission zone reduces the logistics costs despite the need of expensive electric trucks to deliver to micro hubs. Although the proposed model as well as the method has seemed to be useful, there are some limitations to the research. Due to the hierarchical interaction that exists between the two subproblems, the solution can be further improved in future by incorporating improvement heuristics into the iterative solution algorithm. Ideally, heterogeneous vehicle fleets are usually employed by logistics service provider, which are presently not compatible with the proposed model. Finally, the model in this research was applied on a synthetic case study, which necessitates the need in the future to apply it on a real case study. This marks the end of the presentation. I hope you found it interesting. If you have any questions, please feel free to reach out to us. Thank you.